What I want to begin with is sarcopenia, or loss of skeletal muscle mass. If you look at the different complications of cirrhosis, is actually the most frequent complication. More importantly, over the last 10 years or so, we have kind of plateaued, at least in the United States, at the number of transplants that we can do per year. Whereas the number of cirrhotics keeps increasing, resulting in what's called an inverse funnel effect, where the number of non-transplanted patients is going to keep increasing, and they're going to have this major issue of skeletal muscle loss. Now, even if you get on the transplant list, there's no guarantee that you're going to get transplanted, because over 80% of patients who are on the transplant list are waiting for 6 months or longer, during which time they continue to lose their muscle mass. Now, there are a number of studies, including some by Dr. Murali's group and Dr. Murali herself, which have shown there is a reduction in survival in patients with cirrhosis who have a loss of muscle mass measured by different methods. And it also affects the outcomes after transplantation. What we showed was that not only is there loss of muscle mass while patients are waiting for or before transplant, but even after transplant, they continue to lose muscle mass, and patients who lose muscle mass after transplant also die more than transplanted patients who either maintain or increase their muscle mass. So what I'm going to do is, I've already shown you that the clinical significance of sarcopenia is extremely high in cirrhosis. The mechanisms of sarcopenia, we believe one of the mechanisms is ammonia, which inhibits protein synthesis and possibly accelerates protein breakdown. And I'm going to show you some of the functional consequences of hyperammonemia on the skeletal muscle. So as I said, sarcopenia is the most frequent complication. It affects nearly everyone with cirrhosis. It adversely affects outcomes, which are survival, post-transplant outcomes, complications of cirrhosis, and quality of life. Over the last several years when I've spoken, I've always said that there are no effective therapies because the mechanisms are not known. So I've modified that now, and now I say that the mechanisms are not fully identified. And I'm going to show you why I say that. So to understand the mechanisms of muscle loss, I want to first start by saying skeletal muscle mass is maintained by a balance between protein synthesis and protein breakdown, and satellite cell function, which I'm not going to talk about today, but these are the regenerative cells in the skeletal muscle, and that's a totally different topic. So there are two major genes that regulate protein synthesis, which are myostatin, which is a TGF-beta superfamily member, and we've been interested in it for over 15 years now. Insulin-like growth factor, which is synthesized locally and not the one that is released by the liver. And it's believed, or at least used to be believed by the muscle field, that the ubiquitin proteasome pathway is the dominant mechanism of protein breakdown in the muscle, and not much was known about autophagy and the skeletal muscle. So what we did was we took patients with cirrhosis and controls who were undergoing abdominal surgery, got muscle biopsies, and we observed that myostatin, which is a muscle mass inhibitor, was significantly increased in patients with cirrhosis. What was interesting was that when we looked at the ubiquitin proteasome pathway, and we looked at it in a number of ways, I'm just going to show you one specific piece of data. We looked at the message, we looked at protein, we looked at ubiquitination, and we looked at activity. There's no difference between controls and cirrhosis. So the question then that came to our mind was, why is myostatin concentration high or expression high in the cirrhotic patients? I have to say that there is a separate group from Emory which has shown that circulating concentrations of myostatin are significantly higher in patients with cirrhosis compared to controls. So we were interested to see if ammonia somehow modifies, and there are a variety of reasons for that, but in brief, what we saw was that the plasma concentrations of ammonia were significantly higher in transplanted or patients who were waiting for transplant compared to controls. And when we measured the tissue concentrations of ammonia, we found that it was 1 log higher, 10-fold higher than the plasma concentrations in the muscle of these cirrhotics. So we're talking about 5 to 5.5 millimoles per gram of protein of ammonia in cirrhotics. So this is critical because when we were developing our cellular model, we wanted to make sure we were able to reproduce what the human concentrations are. So before we went to a cellular model, we wanted to confirm some of these findings, and we chose the portaceous anastomosis rat and what I would call as the doyen of portaceous anastomosis in the audience, Roger Butterworth, who helped me a lot with Andy Bly in my earlier studies. And what we saw was that by 3 weeks after portaceous anastomosis, myostatin expression was significantly increased, both message, these are Westerns, but the message was also increased. The next question we wanted to answer was, does myostatin really play a role in protein synthesis in an hyperammonemic portaceous anastomosis rat? So I wanted to focus on the right side of the figure for now. The red bar is the portaceous anastomosis, and the yellow bar is a sham animal in which we quantify the fractional synthesis rate by looking at the rate of incorporation of tritiated phenylalanine. You can see that the rate of protein synthesis was significantly lower in the diseased animal compared to the sham animal. When we gave follistatin, which is a myostatin antagonist that we generated, we found that we were able to nearly completely reverse the inhibitory effects of myostatin without altering ammonia concentrations. So this is the first proof of principle concept that myostatin plays a role in hyperammonemic, possibly cirrhotic systems to decrease protein synthesis and muscle loss. So till now what I've shown you is that myostatin probably plays a role. Ubiquitin proteasome pathway really doesn't play a significant role. So when we developed our cellular model, what we did was we generated cell systems in which we exposed them to 10 millimoles of ammonium acetate, because this is the concentration at which we are able to get similar intracellular concentrations of ammonia as we saw in the skeletal muscle. Now you can see here that when we looked at myostatin, muscle IGF, and atrogen, which is a critical component of the proteasome pathway, ammonia specifically increases myostatin message and myostatin protein. Now, I was asked, how do you know that it is ammonium and not the acetate that's doing this? Because we know that acetate can cause epigenetic changes. It has its own signaling properties. So we did experiments with sodium acetate and acetic acid and showed that neither the message nor the protein changed in response to these, demonstrating that it is because of the ammonium. The next question that we were asked, and I didn't do this, I didn't want to do this, but I was made to do this, is to measure intracellular pH in response to ammonium acetate. And I want you to see that the blue bars are ammonium acetate, the red ones are controls. And you see there's no difference between the red and the blue. The green ones are in response to ammonium chloride, which is well known to change intracellular pH. And you can see that there is an initial rapid increase in intracellular pH followed by a steep drop in intracellular pH. And the mechanisms of these are actually pretty well worked out. So I'm not going to go into the details. All I want to say is that we also wanted to prove that our fluorophore system using BCSF was working is by using nigericin, which is a potassium hydrogen ionophore blocker, to say that we can actually say that the system works. What we are measuring is actually real pH in the cell. We then looked at the protein synthesis in the myotubes in response to ammonium acetate, and we saw that the ammonium acetate is decreasing the protein synthesis rate by close to 66%. And we've confirmed this by other readouts using pyromycin incorporation protocol. The next step was to identify how exactly does myostatin work downstream. We're going to look at upstream, but we wanted to see how it works downstream. So in response to ammonia, what we saw was phosphorylation of AKT was unchanged, but phosphorylation of mTOR and P70S6KN4EBP, these are critical canonical protein synthesis regulatory molecules, are all significantly decreased. And we also found that AMP kinase, which is a direct inhibitor of mTOR, independent of AKT, is increased. Based on this, we generated this model that ammonia increases the transcriptional expression of myostatin, which then works through an AMP kinase dependent suppression of critical protein synthesis molecules with a reduction in protein synthesis. And if we block myostatin, we can actually reverse these changes. So now how does hyperammonemia regulate myostatin transcription? So we did some promoter analysis, and Mike Norenberg was actually pretty helpful. He talked to me a number of times about what experiments he had done on demonstrating an increase in NF-kappa B. And these are confocal reconstruction images of the nucleus, in which on the right side, or the left side, you see the whole nucleus. On the left side, there's actually a pie-like slice that has been taken off from a part of the nucleus so that you can look at the nucleoplasm. And what we see is that within 1 hour, the NF-kappa B, which is shown as green dots, increases significantly inside the nucleus compared to TNF-alpha, which is one of the most potent NF-kappa B inducers. So we then looked to see how does NF-kappa B that goes into the nucleus, does it do anything to the myostatin? So we did electrophoresis mobility, shift assays. We did CHIP followed by CHIP PCR, chromatin immunoprecipitation followed by chromatin immunoprecipitation PCR. We generated a full-length deletional constructs of the myostatin promoter. We looked at P65 knockdown cells, and we showed that if you take away P65, myostatin doesn't go up with ammonia, and P65 goes inside, binds to the myostatin promoter, and increases myostatin transcription. We then wanted to see how exactly does ammonia increase P65. So we looked at IKK activity assay, and we showed that IKK activity goes up. IKB, which is the target of IKK, gets phosphorylated, degraded, releases P65, and goes into the nucleus. Based on this, we generated this model that ammonia goes into the muscle, causes phosphorylation of IKB through an IKB-dependent classical NF-kappa B activation pathway, causes IKB degradation, P65 goes into the nucleus, binds to the myostatin promoter. We identified the promoter locations, we deleted it, mutated it, we published all these, and then increases myostatin RNA and increases myostatin protein, which results in inhibition of protein synthesis. So this is the first part of the story. The second part is, what about degradation? Because protein synthesis alone, blocking protein synthesis alone cannot cause muscle wasting. It can only cause failure to grow muscle mass. So we looked at, we already showed that proteasome pathway is not altered. So we looked at autophagy, and we looked at three static markers, P62, Becklin, and LC3. P62 gets degraded during autophagy, Becklin overexpresses, and LC3 gets lipidated, which is the lower bar. All of these increase in human skeletal muscle in cirrhosis compared to controls. We see the same thing happen in the portocaval anastomosis rat model. Same thing happens. In this case, what we went further was, we did what's called an autophagometer, because there are concerns in the autophagy field that static markers are not very good. You need fluxes. So we measured in vivo flux of autophagy using colchicine and ammonium acetate, and we showed that the flux increases in response to ammonia in mice that were made hyperammonemic by IP injections. We then did some cellular experiments where we transfected the myotubes with GFP and M-cherry, two different markers, to see the location of the autophagosome. The green dot showed that the LC3 is getting lipidated. The red dot showed that it's actually entered into the lysosome, and you can see over time there is a sequential progression. These were once again confirmed on electron microscopy, where we showed that ammonia increases the autophagic vacuoles, and then autophagy flux increases with our chloroquine data. So what I would like to summarize till now is that ammonia upregulates myostatin, decreases protein synthesis in the skeletal muscle. It increases autophagy flux. Now, are there functional consequences, and if so, how? So what we did was, we did some MR spectroscopy in the skeletal muscle of the portocaval anastomosis rat, which is shown on the right side, and we did phosphocreatine and ATP ratio. I'm looking at it. It's actually 1.5 minutes. So these are much lower in the portocaval anastomosis hyperammonemic rat. You jinxed it, Chris. Doesn't want to go. Alright, so we then looked at the effect of ammonia on ATP content. So we measured the ATP content in the muscle, and we saw that ATP content in the muscle of the portocaval anastomosis and sham rats follows an inverse relation. So as the ammonia concentration increases, ATP content decreases. We saw the same thing in the cellular system, where we saw that ATP production decreases with ammonia in the muscle cells. We did all the TCA cycle intermediates. I'm going to just focus on alpha-ketoglutarate, which decreases in response to ammonia in these myotubes. Not only is there mitochondrial dysfunction in the form of ATP production reduction, intermediates are also lower. So we then did some mitochondrial dynamics, which show DRP1 and DJ1, which suggest that mitochondria are getting fragmented, their message goes up, mitochondrial fusion genes go down. These were confirmed with phosphorylation of DRP1, which is a fission marker, so we see that mitochondrial breakdown probably should increase. So we then did some EM, and we saw that mitochondria undergo fragmentation. Now, we then did some FACS analysis where what we showed was that mitochondrial ROS production increases very rapidly and continues to keep staying high. And if we give mitotempol, which is a mitochondrial ROS inhibitor, you can reverse these changes. Finally, when you have an increase in ammonia, muscle strength decreases, and we did some ex vivo experiments in which we did muscle contractility study, muscle fatigue studies, etc. I'm not showing all that, but they're all consistent. So the question was, why does this change? And we looked at the nitration of one of the critical muscle contractile proteins, and we see on IP that the nitration of myosin heavy chain increases. So I'm going to conclude by saying that hyperammonemia is a mediator of the liver muscle axis, and muscle is much more than just a metabolic sink for ammonia. The classical pathway of NF-kappa B activation occurs with hyperammonemia and transcriptionally increases myostatin expression and in turn impairs protein synthesis. Autophagy is activated by hyperammonemia and upstream regulatory steps are being dissected. Mitochondrial dysfunction occurs with increased ROS and decreased production. And I want to thank all these collaborators, both nationally and internationally, who have helped me. And I want to also say that there is a large amount of data that Michaela, who is one of the students with Manuela Murley, who have worked with us, we're very fortunate to have her. She has a poster on beta-catenin and NF-kappa B and how they are regulated by ammonia. And I would strongly urge that you should go and see Michaela's work, because she invested a lot of time and she has generated some really interesting mechanisms by which beta-catenin and NF-kappa B, how they go into the nucleus and how they are regulated. Thank you so much.